Okay, thanks for the kind introduction and thanks for staying till the last session. Oops. I hope we don't suffer any more technical difficulties. Okay, thanks for staying. And today I'm going to talk about a characterization of list regression. This is joint work with Chirag, who is also in the audience here. Okay, let's move ahead. So our this talk can be outlined into 5 parts. So first I'll try to give a brief introduction for pack regression, which probably is familiar to all of you. Then I'll talk about list learning, and we'll talk about the agnostic and the realizable case. And then we'll move to proof of sufficiency. The proof of sufficiency is the construction of the learner. And then we'll talk about the proof of necessity, and we'll conclude with some open questions. Okay, so this is demonstrating regression with a diagram. So you have a feature space X, you have labels from 0 to 1, you have a distribution over X called mathcal X cross Y over the data generating process, you have NIID points from D, and the aim is basically to fit a predictor, which is the regression, which is basically the regression. And here we consider the linear structure in this example, this diagram, and the goal is to minimize the generalization error. So this is the thing. So as one may wonder, as it's familiar to most of you, you can have 2 settings, which is very popular here. You have the realizable case, and you can have the agnostic case. So from diagram, it's clear that in the realizable case, you have a predictor which exactly matches the generating process. And in agnostic case, you do not have that. As one may wonder, that agnostic case is more popular, familiar, because this doesn't require any assumptions. And a hypothesis class is pack learnable if the learner's test error is arbitrarily close to the best hypothesis in H. I didn't give the formal definition here. Yeah, so it's arbitrarily close to the best hypothesis in H. Okay, so the natural question which comes here is what characterization learning, which setup is statistically easier? Since you have stronger assumption in the realizable case, one can wonder that realizable case will be statistically easier. You can learn it with a smaller number of samples. And the realizable pack regression was recently solved by Ijanetias and co-authors in 2023, where they show that H is pack learnable, is realizable pack learnable if and only if the gamma yg dimension is finite for all gamma. And for agnostic case, we have an old theorem, there's an old theorem which says that it is agnostically pack learnable if the gamma fat-shattering dimension is finite at all gamma. Of course, one can wonder, and they had also shown that gamma yg dimension is smaller than gamma fat-shattering dimension. Precisely, they had given an example where gamma yg is 1, but the gamma fat-shattering is infinite. Okay, so with this, we now move on to list learning, where the aim is basically to predict, I think I should not hold it here, where the aim is basically to predict a list of items. And this has been of some recent interest, where why study list learning? So you can study list learning because you may want to output a short list of predictions. For example, recommendation systems, that you output a short list of predictions, and at a later stage, you decide which one of the predictions to use. You can consider another example where the training data consists of labels which have been mixed from different units. So you can't basically give one prediction. So a key point here is our list learner outputs from mathcal X to 0, 1 raised to k. However, every hypothesis in the hypothesis class is still a map from mathcal X to 0 to 1. So this will be very crucial as we move ahead later. Okay, so with this, since we are predicting a bunch of k items, we also need to define what the test error will be. So a simple example is this. Say you have data point xy and the predictor mu x, which is predicting 3 items, k equal to 3, 0.1, 0.2, and 0.4, and say the true label is 0.41. The error is basically given by the best label in the predictor. So 0.4 is the best label, and it's given by 0.41 minus 0.4, that's 0.0. So formally, you can just write it as the test error as minimum of IND mu I x minus y. So the question again comes here, same exactly as that has been studied before, that what characterizes learnability in list regression, and we answer both the questions, agnostic and the realizable case. Okay, so this is a diagrammatic representation of what we do. We have the gamma fast shattering dimension, and we propose this generalization, we call it gamma k fast shattering dimension. We have the gamma OIG dimension. We propose this generalization, which is the gamma k OIG dimension for agnostic and realizable case. For k equal to 1, naturally gamma k will be identical to gamma fast shattering dimension, and our theorem basically says that H is agnostically packed k-list learnable if gamma k fast shattering dimension is finite for all gamma. And for the realizable case, we have a very similar theorem which says that it's realizable packed k-list learnable for regression if the gamma co-OIG dimension is finite at all scales. Again, one can observe that these constructed dimensions would be smaller than the original dimensions, as list learning should be statistically an easier problem. Yeah. Okay. Now let us try to go to the definitions of these dimensions, and as often these dimensions are defined, they are often defined in terms of the largest set that can be shattered. So a diagram can explain this very well. So for fast shattering, you can basically say that there should exist C1, C2, C3 such that you have all possible color combination of hypotheses. So basically, a set S is shattered if the projected math-cal-H on S consists of all possible color combinations. So you should have all possible color combinations in fast shattering. In gamma 2 fast shattering or gamma k fast shattering, we have two real numbers on each axis. And so basically you have 3 colored labels along each vertical line, and you should have all possible color crossings. And if you have all possible color crossings, then you will have your hypothesis class is gamma 2 fast shattered on S. So one can see that this is basically a very natural generalization of gamma fast shattering to gamma 2 fast shattering. That for each vertical axis, for each x's, you have 2 points. We call it C12 and C12. And of course, you have this gamma by 2 separation, which is the scale of the dimension, also holding true here, and you have these labels here. Okay, so if this diagram explains better, we can just say this very formally. This is basically a very formal representation of what was said in the diagram in the previous slide. That there should exist these real numbers Si such that for all b in 0, 1, 2d, you have hb of Si either crossing it or below it. And very similar thing can also be said for the gamma k case. And this is just a formal definition of the set of threshold vectors that are permissible. So the threshold vectors are permissible if any pair of components of this vector S is separated by at least 2 gamma. This will be useful, as we shall see later. So this is a very simple example. A very simple example which says that you can have gamma 2 fast shattering dimension to be finite, but gamma fast shattering dimension to be infinite. This is a very simple example. You can just see that for each label 1, you have 0.1, 0.2, 0.3, 1 and 2, you have this. For all things beyond, you just have 2 labels. And one can observe that this has infinite gamma fast shattering dimension for all gamma less than 0.5, but only 1, 2 is the largest gamma 2 fast shattered set. So simple agnostically unlearnable class may be list agnostically learned. So this is a simple hypothesis class which demonstrates the thing which we discussed previously. Okay, so now we move on to the proof of sufficiency and the proof of necessary case. So the proof of sufficiency naturally follows by a construction. And as we all know, and it was also discussed in the previous talk, that for simple regression, a ERM-based learner works. Right? You can just do ERM and it works. This is a known result. However, for our list regression case, we do not exactly know what hypothesis to learn to use for ERM. Because, as we discussed previously, our hypothesis class is still from math-cal-X. Every hypothesis in the hypothesis class is still from math-cal-X to 0 to 1. So we directly don't know on what hypothesis to learn the use ERM on. And this is a key difference from this list paper, which had actually used this hypothesis class to be a list function class. And we actually, this is an open question, but we use a construction from one inclusion graph below. Okay, so the construction of our learner is a bit different, and we invoke partial hypothesis class to construct our learner. So a partial hypothesis class, I'll just recap it. It basically, there is a hypothesis which can predict star undefined for an input xi. It can just say that I don't know. So the key 4 steps of our proof can be described as follows. First, we construct an alternate partial hypothesis class, which moves from the hypothesis class that we had. So the initial hypothesis class was only on mathcalx, but the partial hypothesis class is on mathcalx cross this threshold vector set, which we had defined previously. It's all the set of permissible threshold functions for any hypothesis. And then we create a weak learner on it. This weak learner, again, is created using OIG-based learner. We basically now boost this learner. You can use min-max game or boosting to create a strong learner from this weak learner. Now the important thing which comes is that since it was a multi-class partial hypothesis class where the predictions were integers, we have to convert these integers to a real valued prediction. That involves an algorithm which we call merge list. And finally, using the generalization of the compression lemma, we showed that this generalizes to the case. So this is the construction of the learner. This is basically summarized using these 4 key steps. And the proof of finiteness is also a bit different. And this uses a notion of strong fat shattering that was defined by Simon in 1997. And we use this strong fat shattering as an intermediate tool. So the strong fat shattering, so we basically show that proof of necessity of the finiteness of a related quantity, call it gamma k strong fat shattering, for a learnable list hypothesis class. So we show that this is finite. Then we consider a discretized version. We then show that the strong gamma k strong fat shattering upper bounds a higher order packing number, which we are not formally defining for lack of time, up to constant factors. And then we finally show that this gamma k fat shattering lower bounds the higher order packing number. And this basically concludes the proof showing it's finite. So we leave a lot of open questions here that can a ERM-based learner work for agnostic list pack learner? Simple methods that we tried, like tensorization and other simple things didn't work. So this is an open question, and happy to take questions.
Okay, we have time for a couple questions.
So you only consider like the absolute value loss, or what about the squared loss?
In this paper, considered absolute value loss, but we strongly believe that even squared loss, well, like it's not very difficult to prove, make these arguments for squared loss.
And I guess what is the, I guess in the agnostic setting, you get like a 1 over epsilon squared. I guess actually not necessarily, depends on the, never mind. Yeah. You actually don't always get 1 over epsilon squared for regression.
So you did give an example where I guess the 1 fat shattering dimension was infinite, but 2 goes to finite. So is there some way to understand like how the sample complexity improves generically as k increases? Or?
So the sample complexity will be for function of this gamma k fat shattering dimension. So the sample complexity will be given by what is the like for k equal to 1, if you want to do list learning for k equal to 1, you will be given by gamma fat shattering, k equal to 2, it will be gamma 2, and like that. So it depends on those.
Yeah, okay. I guess I was wondering if there's a way to sort of generically understand like the rate of
so basically you are
decay
saying
with
how
the
does
dimension.
gamma 2 fat shattering is a function of gamma fat shattering,
or something
gamma
like
3, like is there
but you show there's some infinite gaps, so maybe.
Yeah, we just show that there's an infinite gap. We don't have a formal bound saying that, okay, gamma 3 is at most this much than gamma 2 and stuff like that.
Okay, great. Let's thank the speaker again.
Thank you.